Hello, hello. So here we are, chapter 14. Chapter 14, it's a doozy of a chapter. I think in Stat 512, there's kind of maybe two lectures that can be a bit challenging. One of those is well behind us, right? That is the lecture on partial F tests, right? You have that type 1 process, type 3 F tests, chunkwise F tests. Um, that's sometimes a lot to have to absorb, kind of how all those work, the different formulas, and so forth. Um, Probably the maybe second most challenging lecture of the course is the one that we're kind of gearing ourselves up for, kind of starting to kind of mentally psych ourselves up. And that's regression diagnostics. Um, as I'm narrating it, I've broken it into some pieces to make it a little bit more digestible. But in a classroom environment, this is over 100 slides. So um, despite having a 4-hour class, this is typically a class of just 4 hours of straight lecture. That is, there's not even time for a lab, sadly. Um, Now we will see when we get to the end of all these diagnostic PowerPoints, I have kind of figured out how to do this kind of nice surrogate lab, which will give you like a kind of an example and some extra practice, and we'll kind of talk about that. Um, but in some way, I think it's a little advantageous to us that we maybe are getting this in this kind of narrated online environment. 4 hours of just pure nonstop. It's a lot to have to absorb. But here you have the luxury of kind of just doing like a little bit at a time. And I have broken these PowerPoints into 5 different chunks, 5 different pieces. Each piece should probably be less than an hour. And I don't know about you, but my brain is usually kind of geared towards processing about like maybe 50 minutes or so of lecturing, and then kind of starts to shut down. So um, hopefully this should kind of accommodate that type of learning style. Also remember, in particular, you do have supplemental resources. Ideally, you have the textbook. So, I mean, I encourage this for all the chapters, but particularly for chapter 4, supplement what you're learning through this narration by actually reading through the PowerPoint. This is probably one of the most important and also maybe one of the most challenging of all the course lectures for us to get through. So let's go ahead and get started. So regression diagnostics, what are regression diagnostics? Regression diagnostics are statistical techniques designed to detect conditions which can lead to inaccurate or invalid regression results. Big picture, diagnostics are kind of part of a larger process, right? And so this larger process works like this. The first part is checking your data for errors, right? We have some exposure to this from Stat 511, but we'll talk about it in greater detail. In fact, that's sort of step 1. That's the entirety of this particular PowerPoint. The second PowerPoint is going to be all about outlier detection. The third and fourth PowerPoints are all about checking our 4 assumptions. Sometimes that step 3 is thought of as the actual diagnostics, right? These sort of statistical techniques for looking at situations where our regression's not warranted, or might be invalid, or might give us misleading results. That's essentially saying like, well, are our assumptions satisfied? And then that fourth process, which will be the 5th PowerPoint, is detecting the presence of something called collinearity, also sometimes referred to as multicollinearity. Means the same thing. So let's start with this idea of checking the data for errors, right? I mean, big picture, I like to think of this as just getting yourself acquainted with your data set. And we'll see there's lots of reasons to do that. There's lots of value in doing that. It's one of those things that's a little bit hard to kind of to set up in a classroom environment. But as you transition from the classroom to the workplace, I think that you'll become kind of more and more aware of the importance of doing this. And I would say with any data set, all right, go through these kind of steps that we're going to talk about. Know your data set, learn your data set, become very intimate with your data set. But even like more big picture, right? Some very common and I think very valuable statistical advice is like once you've gone into the workplace, right? Once you've found a job, an industry that you're happy with, right? More broadly than equating yourself with the data set, like equate yourself with like the field that you've embedded yourself within. That is, if you're a financial data set and you tend to find yourself dealing with data sets that say have variables like GDP or various term interest rates, then what do you want to do? You want to actually start Googling, you want to start reading, you want to start learning more about, well, what is GDP? How does it work? How is it constructed? What are these different interest rates? How does one differ from the other? What are they derived from? Kind of what does conventional wisdom say they're sort of intertwined with? All right, this is all part of like being a good, effective statistician. And again, part of it is you have to embed yourself in your field first to be able to do this effectively. It's part of why it's hard to do in a classroom. But nonetheless, I'm going to try to give you some steps to think about to kind of help start getting us there. So when we get a data set, when we inherit a data set, when we're past a data set, a couple things to think about, right? Number one, what is the experimental unit? That is, when I'm looking at my rectangular data set, I have these rows. What does a single row correspond to? Does a single row correspond to a person? Maybe a single row corresponds to a family. Maybe it corresponds to a city block. Maybe it corresponds to a state, right? This is important. In fact, right, I know in my class, right, in the midterm we just took, right, there was a question talking about like gas consumption, and there was like a little bit of confusion about the problem and a few people asking questions. And what really kind of, I think, cleared it up was making it clear that in this particular data set, an observation was a week, right, in Philadelphia. So a single observation was how much gas was consumed in that week and what the average temperature was for that week. So we had like 8 observations. Essentially, it was like a data set that was 8 weeks in Philadelphia. So in that example, our experimental unit was a week. Step 2, right? What was the process used in terms of collecting this data? Where did the data come from, right? Data don't just sort of like don't just spontaneously create themselves. They're derived in some way. They're collected in some way. How? Number 3, right? Look at each variable and ask yourself, like, what are the units that this variable is being measured in? If the variable is temperature, okay, we all know what temperature is, but are we measuring that in Celsius or are we measuring that in Fahrenheit? If the variable, right, this goes back to a lab, if the variable is, say, the number of half bathrooms in a house, right, we want to ask ourselves, okay, are we measuring a half bathroom as like 0.5, or are we measuring a half bathroom as 1? There's 1 half bathroom. Right? How is this variable being measured? That number 3 kind of feeds into 4, right? 4 is, right, what are plausible ranges of values? What's a typical value? So, right, again, a plausible range for temperature is going to depend, right, whether it's Celsius or Fahrenheit. Each of those ways of measuring, each of those units of measuring temperature is going to have a different range of sort of reasonable values. And then number 5, right, what's our sample size, right? Essentially, we're talking about how many rows in our data set, and are there any missing values? So why do we care about this? What's the point of doing all this, right? What are we going to do with it once we get this information? Well, experimental unit, sampling design, and variable information, right? Particularly, is this a categorical variable versus a numeric variable? and the size of your sample all help you determine the appropriate type of statistical test, right? So for example, right, stat 512, that y variable has to be continuous. If instead our y variable is categorical, we would use a whole other set of statistical techniques. To get an appreciation of like sampling design, that is how the way the sample was gathered might dictate how you analyze the data. It is a big deal, and we maybe don't have an appreciation of it yet in 512, but when you take stat 514 next year, that whole class is kind of about, right, the importance of sampling design and how that dictates the way you look at or analyze a data set. Knowing units of measurements and plausible ranges helps us determine if there's been data collection errors. We'll talk more about that in a little bit. Now, what about the missing data, right? I think this has probably been drilled into us pretty well in Stat 511, so we'll try to go through it somewhat quickly, right? But missing data is important to know for a variety of reasons, right? Depending on why the data is missing, it could bias your results. So that's something that we want to think about, right? That is, maybe we're testing some kind of weight loss regimen or maybe some kind of weight loss supplement. And maybe like a bunch of people dropped out of our study. I don't know, a little bit extreme, but maybe, for example, half of the people dropped out of our study. And so we look at the half that we have, and if we look at the half that we have, well, they lost a lot of weight. And so it might be tempting to conclude, hey, this regimen, the supplement, is really effective. But we certainly want to be cognizant of what? We want to be cognizant of the possibility that the people that we don't have information for, there's a reason we don't have their information. We don't have their information because they dropped out of our study. Why might they have dropped out of our study? They might have dropped out of our study because the supplement wasn't working for them. Right? They got frustrated and it wasn't working. Who knows? Maybe their weight even went up. And because of this, they said, screw it. I'm not going to bother with, right, whatever this regimen is, this kind of this imposition of inconvenience on my life. And so, right, that we can hopefully see that might introduce a bias. That is, we're only looking at the half of our data set that was successful and kind of ignoring the half of our data set where it was unsuccessful, and probably getting a rosier picture of how effective this thing might be, right? These are big picture important concerns that we as statisticians want to be sort of cognizant of. We want it on our radar. Now, of course, we also know from 511 that missing data is really important, and we need to always keep it in mind when we're writing our SAS code. All right, so consider a data set where we have the number of credits for 90 out of 100 college students. The other 10 have missing values. And we want to use this information to create another variable, student type. So we'll take the number of credits, and then those number of credits will tell us whether someone's a freshman, a sophomore, a junior, or a senior. And so here's some code. I whipped it together, not to brag. I'm a little bit of a SAS programming expert. So if the credits are less than equal to 30, well, that sounds like a freshman to me. If they're between 30 and 60, right, we would define that as a sophomore, right? This is talking about undergraduates. Between 60 and 90, or a junior, and anything more than 90, right, we call that a senior. All right, if you're, I guess, over 120, you're a, I don't know, you're a wizened senior, a grand senior. Pretty good code, right? Yeah, all right, fair enough, right? You don't have to all pile on me. I agree. This is actually some poorly written code, isn't it? We should have done what? I mean, there's a few different ways we could have improved this. Right, we could have used else statements instead of 4 different if statements. That's a little bit more efficient coding. But probably the most egregious error is that first line, right? Because what's that first line doing? Remember, SAS is a little quirky about how it internalizes missing values. It internalizes missing values as like a really, right, quote, large negative number. So actually, it would interpret a missing value as being less than 30. And so what this code would do is it would take those 10 people, we don't know what their credits are, right? They may or may not be freshmen, but regardless, it's going to label them as freshmen, right? And that's bad. We don't want to do that. We can fix it in a lot of different ways. Maybe the easiest way is to just say if the credits are between 0 and 30, right? Then type equals freshman. So again, right, acquainting ourselves with our data set and seeing those missing values, right, helps us know we need to be really careful, right, with how we kind of write our code. That said, I would actually encourage us to always write code that would work well, work well if we have missing values, even if the data set we're working with at the time doesn't have missing values, right? Because the idea is we want to be able to reuse our code. You get a new data set, let's use the same code. We get a new data set, let's use the same code. So even though the data set we're using today doesn't have missing values, right, that doesn't mean the data set we're not going to get tomorrow might not have missing values. And if that's the case, right, the code that I wrote earlier, if I didn't write it in a way to accommodate missing values, right, could get me into trouble. So, all right, again, Stat 511 101, always write your code, right, as if you might have missing values. Don't be careless with your code like I was here on slide 8. Yeah, we already answered that question, didn't we? So once we're sort of cognizant of missing data, right, the next step we might do is go ahead and check our data for errors. How do we do that? It's often done with simple descriptive statistics. Now, of course, remember, anytime we're bringing our data set into SAS, right, as part of that getting acquainted process, we should look at our log window, right? The log window has a lot of nice information. We can run proc contents, that has a lot of nice information. We could even run like a proc print. If it's a large data set, we could proc print just a small portion of it, right? All of these things, right, make sure the data was actually imported correctly. And it also helps us get, again, kind of more comfortable with that data set. So how do we generate descriptive statistics? Again, we did this in 511, but just a quick review. For numerical data, we can use proc means or proc univariate. For categorical data, we would typically use proc freq. When looking for like data entry errors, we often focus on like the largest and smallest values, right? The mins and the maxes, right? Maybe to be a little bit more comprehensive, might maybe look at like the 5 largest, 5 smallest. Nothing magical about the number 5, but right, a certain number of the larger values, certain number of the smaller values. Also look at measurements of average and variation. We could also look at plots, right? Plots are very effective at kind of showing us what's going on. You can look at a histogram or a box and whisker plot, something we should be familiar with from 511. It's also in, I think, our review slides from when we started this class. And you could also check correlations between variables, right? So all of these things helping us determine if there's any data entry errors, particularly that first bullet point. But again, also helping us understand what our variables are, right? What's going on, right? Particularly when we're working with like non-statisticians, sometimes like this descriptive information just in and of itself is actually very informative and very useful to them. So, right, it's something that maybe we would consider, right, putting in our report or communicating to our client, right? They might be interested in some of these like averages or maybe some of these correlations. So yeah, so looking at descriptive statistics, particularly the minimum and the maximum, helps us find outliers and or data entry errors, right? Maybe, where did these come from? Well, maybe someone put temperature in Celsius when it was supposed to be in Fahrenheit, right? Maybe the other way around, right? The fact of life is that data entry errors happen a lot, right? Large part of kind of like the rise of this idea of data science is this idea that, right, that just about every quote real life data set is in some way dirty. Right? We have these dirty data sets. And so we need to clean them up. We need to go through this data cleaning process. That data cleaning process starts with finding the errors, and then of course we have to fix those errors. Now again, never forget our plots, right? In statistics, as in life, a picture speaks 1,000 words. So plots have lots of information, and again are a very nice preliminary step to kind of cleaning our data set, getting acquainted with our data set. As we'll see in our next chunk of slides, box and whisker plots are effective for finding outliers. Histograms are good for a whole bunch of different things, but maybe one of those things is like finding possible subpopulations, right? So if you look at a histogram of, say, like heights of students, what are you going to do? You're going to see two peaks, aren't you? The histogram's going to be what they call bimodal, two peaks, two humps. Why? Well, one of those peaks is probably for female students, right? One of those peaks is probably for male students, right? Males tend to, certainly exceptions, but males tend to be larger, taller than females. And so when we see these two subpopulations, when we see these multiple peaks, these multiple modes, that's telling us, hey, there might be some subpopulations that I might want to separate and at least potentially analyze separately. Now, a question I get a lot is like, okay, I find this outlier. I found this number that seems way too large to be realistic or way too small to be possible. What do I do? Well, you check it, right? And again, in a classroom environment, this is hard to do because you're just given a data set by a professor. We're a little disconnected often from the source of our data sets. But in practice, in a workplace where we're less disconnected, we would look into this unusual observation. The first thing is like check it and ask ourselves, is this a data entry error, right? It may be that it's like so out there that we know it has to be a data entry error, right? That is, someone's supposed to rate something between 1 and 10, and the number is an 11, right? And we know that it can't be an 11, so it's obviously an error. Sometimes, right, it's extremely large or extremely small. It's really sort of outside like the sort of range of all the other values in our data set, but it's technically a possible value. That is, it's unusual for a human being to weigh 500 pounds, but there are 500-pound human beings out there. So, right, if you saw a weight of 500, right, it's unlikely, but it's possible. Right? Whereas if someone told you the weight was negative 300, well, negative 300 is impossible, right? So anyways, regardless, check if you can to see if it's possible. If it is possible, double check, like look at the source. Where did it come from? Was there a typo, for example? If everything checks out and it's not a typo, it seems correct, right? If you can, check to make sure that it's part of your population of interest, right? So maybe your study, for example, is supposed to only be for people that have mild asthma. You're working on a drug, that drug is only approved or targeted for people with mild asthma, but for whatever reason, this patient who has extreme asthma slipped through the cracks and got enrolled in your study. They shouldn't have. And because they're not part of your population, right, because they have extreme asthma rather than mild asthma, that's why their number is so much out of the pattern, is such a large outlier. And in that case, right, I mean, they're not part of your population, so you would kick them out. Right? But again, at the end of the day, if you double check it, it's not a typo, and you double check whether they belong in your study and they belong in your study, then, right, even though the number itself is unusual, we still keep it. Right? That is, we're never going to remove an observation just because it's an outlier. Typically, if it's an outlier, we'll fix it if we can. We'll double check it. We'll see if it's part of our population of interest. If it's not, then we would get rid of it. But assuming it is part of our population of interest, we would keep it in our data set. Okay, so that's numerical data, right? What about categorical data? Categorical data, we use proc-freq, right? Proc-freq is, right, we're familiar with it from Stat 511. Next semester, you're probably going to take Stat 507. Stat 507 is categorical data analysis. That class uses a lot of proc-freq, so you'll become even more of an expert on it. But proc-freq we could use to build all these different tables, right? And the tables basically show us the values that that variable takes. So why do we care about that? Well, right, one thing it can show us is that, right, maybe some observations when they wrote big, they capitalized it. In some observations, they didn't capitalize it, right? And to us as human beings, that's not a big deal. But remember, SAS is case sensitive. So SAS would consider that uppercase big different than that lowercase big, and treat that as like sort of two different things, when in reality it's not, right? I mean, both of those are just saying that that person is in the big category. So that's something that it would help us find, and of course after we find it, we would need to fix it, right? Either take the lowercase ones and capitalize them, take the uppercase ones and quote lowercase them, but make them consistent with each other. And then sometimes we find maybe some relationships between variables that give us insight into the problem, or maybe simplify model building. So here's just an example. Maybe an owner of a used car lot hires a statistician to build a model based off historical sales to predict the sales price of used cars. And two variables in the data set are liters and cylinders of the car's engine. So this is based off a real data set, actually. I know zero about cars. I know zero about engines. I mean, I certainly have heard the term liters. I've heard the term cylinders, right? But I couldn't tell you like precisely what they are. Not like a super great auto mechanic. You may or may not be more mechanically inclined. You may or may not be familiar with that, but I'm sure at least some of you are in that sort of same level of cluelessness that I am. And so a frequency table maybe gives us some interesting insight that we might not have otherwise as potential non-experts in engines. Right, so there's our table, right? And we look at it, and this is only part of the table for the record. They're actually, it's like a truncated version. But the pattern that we can observe here holds for the rest of the table. So I think the cylinders were only 4, 6, and 8. I think there were more rows to this table. So we're only looking at some of the rows there. And so what do we see? Yeah, we do, don't we? Notice that if we look at a particular liter, it always, like say 3.1, all of the 3.1s are 6 cylinders, aren't they? And all of the 3.4s are 6 cylinders, and all of the 3.5s are 6 cylinders, all of the 3.6 are 6 cylinders, all of the 3.8s are 6 cylinders, all of the 4.6 are 8 cylinders. So what is that telling us? Exactly. It's telling us that we really don't need both of those variables, right? It's telling us that if you know the liters, you also know the cylinders. So I don't need both of those variables in my model. Agreed? And you might say, well, who cares? But that actually is a pretty big deal. We'll maybe get a better appreciation of why that's a big deal when we do our next lecture on model building. But I feel like we have like a little bit of insight into it now, right? Because what? We know there's these interactions, and right, we've at least had a little bit of experience with like polynomials. So eliminating one variable, say like cylinders, is actually maybe eliminating like a bunch of variables, right? Because it's eliminating all the interaction terms that involve cylinder. Maybe polynomial terms. May or may not put a polynomial thing in there, but I mean, we might consider it at least. But we don't need it if we get rid of cylinders, right? So getting rid of the variable cylinders, right, can actually greatly simplify our model building process. So it's kind of catching this at an early stage will help us when we go to the next step, which is, right, this model building step, right? In particular, for this example, we see as we go to the model building step that we don't even need to worry about the variable cylinder. We don't need that in our model. We could just put liter. Because, right, knowing the liter determines the cylinder. Yeah, pretty cool, right? Yeah, we already made our observations. So again, these are standards of good practice before beginning any statistical analysis. They're not restricted to 512, right? This is like more big picture, right? Maybe like from a consulting perspective, just from a, hey, I got a data set, I've got a problem that I want to work with, I want to solve. Let me kind of see what's going on with this data set. I want to get comfortable with the data set. I want to understand what this data set is doing. I want to look for errors or problems in this data set so I can go about cleaning my data set. I think the kind of like the new age term that they're using these days for this kind of thing is like data wrangling even. So we're gonna wrangle our data. Makes it sound a little bit like cowboys and cowgirls, doesn't it? All right, so that's 1 out of 5 diagnostics slides done. So why don't you maybe take a little bit of a breather, and then I'll see you for part 2 in just a little bit.